Okay, okay. Wonder if this is working. Who knows? Who knows? Certainly not a she go. All right, all right. Let's just pop that out here. Should probably have gotten this out beforehand, but bit late today getting started. All right, right, right. Pop out you. Where's Chromie? Here she is. All right, I'm pretty certain that we were. Yeah, we're starting fearless concurrency. Now, this is exciting multi-threading. As a JavaScript dev, this is my vein. This brings me great fear, for I don't know what the fuck I'm doing. Got something to do with string, I think? That's okay with me? Oh, okay. Just gonna take a moment before we get started on the reading. I don't know how long it's gonna take me, just a moment, I guess. Here we go. I keep saying these words come out of my face and nothing happens. Alright, right. Okay, so we are currently going on fearless concurrency. I am assuming that this is going to be just multi-threading, but there could be something else. Using threads to run code simultaneously, using message passing to transfer data between threads, shared state concurrency, and extensible concurrency with the sync and send trait. So yeah, this is just talking about concurrency. Mostly multi-threading, though. I wonder if you can do this. No. Yeah. This is going to just be about multi-threading. You can do a. I guess that's not really concurrent. Never mind then. All right, I'm just going to start reading from square one. Fearless concurrency. Handling concurrent programming safely and efficiently is another of Rust's major goals. Concurrent programming, where different parts of a program execute independently, and parallel programming, where different parts of a program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. Historically, programming in these contexts has been difficult and error prone. Rust hopes to change that. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. Oh, okay. I'm glad that's what they're doing. How, though? Well, I guess we'll learn. Therefore, rather than making you spend lots of time trying to reproduce the exact circumstances under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. As a result, you can fix your code while you're working on it rather than potentially after it has been shipped to production. We've nicknamed this aspect of Rust fearless concurrency. Fearless concurrency allows you to write code that is free of subtle bugs and is easy to refactor without introducing new bugs. Okay, So what I am going to guess is going to happen, just as a bit of a hypothesis to start out with this. What it's going to do is similar to what it does with ownership, making us resolve every single possible chain which we can undergo through concurrency before it allows us to compile. At each point telling us where we have missed. Is this what's going to happen? If so, I'm really curious to see it. Note, for simplicity's sake, refer to many of the problems as concurrent, rather than being more precise by saying concurrent and or parallel. If this book were about concurrency and or parallelism, we'd be more specific. For this chapter, please mentally substitute concurrent and or parallel whenever we use concurrent. Many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang has elegant functionality for writing message passing concurrency that is but has only obscure ways to share state between threads. Supporting only a subset of possible solutions is a reasonable strategy for higher level languages, because a higher level language promises benefits from giving up the same control to gain abstractions. However, lower level languages are expected to provide the solution with the best performance in any given situation, and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. Here are some of the topics we'll cover in this chapter: how to create a thread, and run multiple pieces of code at the same time; message passing concurrency, where channels send messages between threads; shared state concurrency, where multiple threads have access to some piece of data; the sync and send traits, which extend Rust's concurrency guarantees to user-defined types, as well as types provided by the standard library. Okay, so sync and send, I'm guessing, are going to be traits where we define how to act when we do message passing with send, or shared state concurrency with sync. And I'm assuming that they have to follow some structure. Well, of course they have to follow some structure, but I don't really know where I was going with that, honestly. Let's go forward. Using threads to run code simultaneously. In most current in most current operating systems, an executed program's code is run in a process, and the operating system will manage multiple processes at a time. Within a program, you can also have independent parts that run simultaneously. The features that run these independent parts are called threads. For example, a web server could have multiple threads so that it could respond to more than one request at the same time. Splitting the computation in your program into multiple threads to run multiple tasks at the same time can improve performance, but it also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order in which parts of your code on different threads will run. This can lead to problems such as race conditions, where threads are accessing data or resources in an inconsistent order; deadlocks, where two threads are waiting for each other, preventing both threads from continuing; bugs that happen only in certain situations and are hard to reproduce and fix reliably. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in programs running a single thread. Programming languages implement threads in a few different ways, and many operating systems provide an API the language can call for creating new threads. The Rust standard library uses a one-to-one model of thread implementation, whereby a program uses one operating system thread per language thread. There are crates that implement other models of threading that make different trade-offs to the one-to-one model. Okay. I'll admit, my understanding of multi-threaded programming is lacking. How would a 1-to-2 thread model work? Or I'm really curious how that works. Like, is it like a 1-to-2 for each language thread? There are two system threads, or are there crates that have for each 2 language threads, 1 system thread. I'm curious how to see that work. Creating a new thread with spawn. To create a new thread, we call the thread spawn function and pass it a closure. We talked about closures in chapter 13, containing the code we want to run on the new thread. The example in listing 16.1 prints some text from a main thread and other text from a new thread. We have thread spawn taking in nothing with the function of for 1 in the God, what is that iterator? Why did I forget that word? For 1 in the iterator of 1 to 10, print line high number from the spawned thread, outputting I. Thread sleep duration from millis 1. So sleep for a certain amount of milliseconds. And then after this, yes. Oh, and then we have after the thread is spawned 1 to 5, print high number from main thread I. I'm guessing it's just going to have a bunch of random numbers being pasted. 1 from main thread, 1 from spawn thread, 2 from main, 2 from spawn thread, 3 from main, 3 from... Well, yeah, I guess so, because of the sleep. Alright. Note that when the main thread of a Rust program completes, all spawn threads are shut down, whether or not they have finished running. The output from this program might be a little different every time, but it will look similar to the following. Hi for number 1 from the main thread. Yep, and it will go down like that. Of course, if there's something wrong with your operating system, or there's just some reason why the second thread has to sleep for a significant amount of time, just some hiccup, it'll be offset by that amount. That's why depending on 1, 1, 2, 2, 3, 3, 4, 4 to be the output would be a bad thing to do. You should not do that. The thread calls to thread sleep. Sorry, the calls to thread sleep force a thread to stop its execution for a short duration, allowing a different thread to run. Oh, okay. Never mind. I guess it would always do that. No, it definitely wouldn't. It would still be offset. Threads will probably take turns, but that isn't guaranteed. It depends on how your operating system schedules the threads. In this run, the main thread printed first, even though the print statement from the spawn thread appears first in the code. And even though we told the spawn thread to print until I is 9, it only got to 5 before the main thread shut down. If you run this code and only see output from the main thread, or don't see any overlap, try increasing the numbers in the ranges to create more opportunities for the operating system to switch between threads. Waiting for all threads to finish using join handles. Okay. It says take turns, but on a multi-threaded CPU, shouldn't they run concurrently? I don't know. On a multi-core, it should, right? The code in listing 16.1 not only stops the spawn thread prematurely most of the time due to the main thread ending, but because there is no guarantee on the order in which threads run, we also can't guarantee that the spawn thread will get to run at all. We can fix the problem of the spawn thread not running or ending prematurely by saving the return value of thread spawn in a different variable. The return type of thread spawn is join handle. A join handle is an owned value that, when we call the join method on it, will wait for its thread to finish. Listing 16.2 shows how to use the join handles of the thread we created in listing 16.1 and called join to make sure the spawn thread finishes before main exits. Yeah, I'm guessing it's just a call to .unwrap. Okay, yeah, so it outputs an option? I'm guessing that the option is output to allow us to return an error, to capture and return an error. I'm assuming? Saving a join handle from thread spawn to guarantee the thread is run to completion. Calling join on the handle block, on the handle blocks the thread currently running until the thread represented by the handle terminates. Blocking a thread means the thread is prevented from performing work or exiting. Because we've put the call to join after the main thread's for loop, running listing 16.2 should produce an output similar to this. I for 1, 2, 1, 3. Yeah, 1, 2, 1, 3 for the main thread, so on and so forth, and allowing it to continue forward. The two threads continue alternating, but the main thread waits because of the call to handle.join, and does not end until the spawned thread is finished. As I said here, yeah, I guess it does in fact sometimes have to wait a bit. Yeah, the spawn thread could have some time running up. Perhaps your CPU is currently busy with other things on your computer. Right. But let's see what happens when we instead move handle.join before the for loop in main like this. Okay, well, it'll stop here. It'll do the entire 1 through 9, or 1 through 10, and then it'll do the 1 through 5, 1 through 4. Yep, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. Well, of course, yeah. Oops. Oh, come on. Alright, where were we? Where were we? I guess we were. The main thread will wait for the spawn thread to finish and then run its for loop, so the output won't be interleaved anymore. Interweaved? I am assuming it means, but who knows? Perhaps interleaved is a correct word here. Yep. Small details, such as where join is called, can affect whether or not your thread run at the same time. Threads run at the same time. Of course, yeah. If it hits join, it's just going to wait until the thread that you've called join on is complete. Using move closures with threads. We'll often use the move keyword with closures passed to thread spawn, because the closure will then take ownership of the values it uses from the environment, thus transferring ownership of those values from one thread to another. In the Capturing References or Moving Ownership section of Chapter 13, we discuss move in the context of closures. Now, we'll concentrate more on the intersection between move and thread spawn. Notice in listing 16.1 that the closure we pass to thread spawn takes no arguments. We're not leaving any data from the main thread in the spawn thread's code. To use data from the main thread in the spawn thread's closure must capture the values it needs. Listing 16.3 shows an attempt to create a vector in the main thread and use it in the spawn thread. However, this won't work yet, as you'll see in a few moments. Right, we got that v equal vec 1, 2, 3. Let handle equal the spawn thread. Use a vector. We cannot utilize it here. Okay, yeah. Makes sense, because it doesn't know that you called joined until it hits here. That could be deleted. Does this? Yeah, this won't compile. Good. The closure uses v, so it will capture v and make it part of the closure's environment. Because thread spawn runs the closure in a new thread, we should be able to access v inside that new thread. Oh wait, yeah, it does capture it. No, it makes sense. But we get this error. Closure may outlive the current function, but it borrows v, which is owned by the current function. Oh, I guess why? Why though? Because at the end of the current function, this cannot actually outlive the current function, can it? Main needs to live longer than handle, which is thread spawned here. Let's ignore this. If main gets to its end before handle dies. How does the closure outlive the current function? Why? To force the closure to take ownership of v and any other reference variable, use the move keyword, of course. Rust infers how to capture v, and because println only needs a reference to v, the closure tries to borrow v. However, there's a problem. Rust can't tell how long the live thread will run, so it doesn't know if the reference to v will always be valid. Listing 16.4 provides a scenario that's more likely to have a reference to v that won't be valid. Right, so oh, okay. Yeah, okay, never mind. That's fair. Yeah, that's fair. So just to clarify, we are dropping V while the thread is still running. But can't it just know? Why won't it error out here? Like, why? Oh, well, I guess because you could try and borrow it. You could try and take ownership later. If it's just borrowing, you could probably take ownership somewhere else. Perhaps that could then drop it if you take it into new context, but couldn't it just look for that instead of handling it like this? Because it would have to look at that if we moved it, because ownership would be moved here. Like, I'm unsure. If Rust allowed this code to run, there's a possibility that the spawn thread would be immediately put in the background without running at all. The spawn thread has a reference to V inside, but the main thread immediately drops V. Using the drop function we discussed in chapter 15, then when we then the spawn thread starts to execute. My lord, I can't read right now. Then, when the spawn thread starts to execute, V is no longer valid, so reference to it is also invalid. Oh no! To fix the compiler error in listing 16.3, we can use the error message's advice. Use move. By adding the move keyword before the closure, we force the closure to take ownership of the values it's using, rather than allowing Rust to infer that it should borrow the values. The modification in listing 16.3, shown in listing 16.5, will compile and run as we intended. Yep, looks fine. We might be tempted to try the same thing to fix the code in listing 16.4. No, we drop it. You can't drop something you don't own. With a main thread called drop by using a move closure. However, the fix will not work because what listing 16.4 is trying to do is disallowed for a different reason. If we added move to the closure, we would move V into the closure's environment, and we could no longer call drop on it in the main thread. We would get this compiler error. Use of moved value 3. Move occurs because V has the type vec_i32, which does not implement the copy tree. Handle here, move. Value moved into closure here. Variable moved due to its use in the closure. So it tells you both locations. Hey, it would be moved. Oh, never mind. Because we have the move keyword, anything utilized in it will be moved. And here is where it is utilized within the closure. Okay. Value used here after the move. Rust ownership rules have saved us again. Huzzah! I don't know why I said huzzah. I give anyone listening to this, which I highly doubt there are people listening right now, I give you permission to shoot me. We get an error from the code in listing 16.3 because Rust was being conservative and only borrowing V for the thread, which means that the main thread could theoretically invalidate the spawn thread's reference. By telling Rust to move ownership of V to the spawn thread, we're guaranteeing Rust that the main thread won't use V anymore. Sure. If we change listing 16.4 in the same way, we're then violating the ownership rules when we try to use V in the main thread. The move keyword overrides Rust's conservative default of borrowing. It doesn't let us violate the ownership rules. With a basic understanding of threads and the thread API, let's look at what we can do with threads. Got that wrong. Right, will this pass the compiler? We got immutable n1. We have a move saying, hey, take ownership. N equals n plus 1, that's fine. You spawn another thread within a thread, moving n into it. N equals n plus 1. I'm assuming that this thread will not spawn until after this is run. We are now utilizing it here, which means that it will not run because it does not have ownership. It's been moved into here, and even if it has not yet been moved into here, n equals n plus 1 is usage after the movement. Ownership is now within here. That cannot run. Does not compile. How many questions? 2. Consider this example from the text where a vector is improperly captured by a thread. Rust compiler includes this diagnostic. Recall the static is a lifetime of references that are not valid for the entire program's duration. Which of the following best describe the note? Functions require argument type to outlive static. I don't understand. Right, so we have a vector, handle thread spawn. We're trying to print the entire vector within the handle, and then we wait for it to join and unwrap. Rest compiler includes this diagnostic. Gnostic. Function requires argument type to outlive static. Let handle equal thread, right? But we just have some pointers. Yep, thread spawn. Recall that static is the lifetime of references that are valid for the entire program's duration. Which of the following best describes the note? Function requires argument type to outlive static. Vector v contains values which do not outlive static. Rust doesn't know how long a thread will run, so the thread's captures must live forever? I'm guessing that's what it means. A closure may only capture string constants of type reference static string. That's wrong. The closure path to thread spawn is not allowed to take any arguments. I believe this is correct. It doesn't know how long the thread will run, so anything the thread captures must live forever. I guess that's why? That is why. Apparently this will compile. Why will it compile? Why the fuck will that compile? Move keyword causes n to be copied. Because it implements copy, it's just copied. It's not moved. You use the move keyword, but it's not moved, it's copied because it implements the copy trait and you're not forcing it to be. Okay. Yep. So, I hate this. I like explicitity. So n in here is not actually n. It is an entirely different thing. Okay. Yep, because it implements copy. I forgot. I tend to think Rust does things explicitly and makes it very understandable how things work, but nope, in this case it doesn't. However, I should have guessed because continuously it says does not implement the copy trait, so I should have guessed. Because integer implements the copy trait, it'll be copied. And this isn't a reference either. It's not asking for a reference to it, to be clear. It's not creating a reference, so it is simply copied. Yeah, I guess what messes me up, I guess, is also separately that it doesn't have let mutable n here, so it feels like it's actually using n, when in fact, no, it's not. It's kind of shadowing it. Right? The move keyword causes n to be copied in the closure, so the assignment n equals n plus 1 within thread spawn will have no effect on the outer n. Okay. Okay. Context here. If a closure captures a reference to a value that lived less than static, it's possible that the thread would live longer than the value and violate memory safety. Notice that thread scope can be used to allow threads to capture non-static references by statically limiting the lifetime of the thread. Oh, that's good to see. Using message passing to transfer data between threads. One increasingly popular approach to ensuring safe concurrency is message passing, where threads or actors communicate by sending each other messages containing data. Here's the idea in a slogan from the Go language documentation. Do not communicate by sharing memory. Instead, share memory by communicating. To accomplish memory message sending concurrency, Rust's standard library provides an implementation of channels. A channel is a general programming concept by which data is sent from one thread to another. You can imagine a channel in programming as being like a directional channel of water, such as a stream or river. You can put something like a rubber duck into a river. It will travel downstream to the end of the waterway. A channel has two halves, a transmitter and a receiver. The transmitter half is the upstream location where you put the rubber duck into the river, and the receiver half is where the rubber duck ends up downstream. One part of your code calls methods on the transmitter with the data you want to send, and another part checks the receiving end for arriving messages. A channel is said to be closed if either the transmitter or receiver half is dropped. Okay, so I'm guessing what this is stating is that if we have two threads, one thread, two thread, we transmit from this thread, which puts it into a sort of inbox in this thread. If we go through the thread, down, 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 we have to manually check during the thread to see if there are any messages in our inbox. If we don't and just continue on, that message will not be received. This is my guess. Here we'll work up to a program that has one thread to generate values and send them down a channel, and another thread that will receive the value and print them out. We'll be sending simple values between threads using a channel to illustrate the feature. Once you're familiar with the technique, you could use channels for any threads that need to communicate between each other, such as a chat system or a system where many threads perform parts of a calculation and send the parts to one thread that aggregates the results. First, in listing 16.6, we'll create a channel, but we won't do anything with it. Note that this won't compile yet because Rust can't tell what types of values we want to send over this channel. Right, so we have MPSC. What is MPSC? Who knows? We create a new channel using the MPSC channel function. MPSC stands for multiple producer, single consumer. Okay. In short, the way Rust standard library implements channels means a channel can have multiple sending ends that produce values, but only one receiving end that consumes those values. Imagine multiple streams flowing together into one big river. Everything sent down any of the streams will end up in one river at the end. We'll start with a single producer for now, but we'll add multiple producers when we get this example working. The MPSC channel function returns a tuple, the first element of which is the sending end, the transmitter, and the second element is the receiving end, the receiver. The abbreviations TX and RX are transmitting and receiving X are traditionally used in many fields for transmitter and receiver respectively. So we name our variables as such to indicate each end. We're using a let statement with a pattern that destructures the tuples. We'll discuss the use of patterns in let statements and destructuring in Chapter 18. Currently Chapter 17. 16 actually, that's quite a while away. For now, know that using a let statement this way is a convenient approach to extract the pieces of a tuple owned by MPSC channel. Let's move the transmitting end into a spawned thread and have it send one string so the spawned thread is communicating with the main thread, as shown in listing 16.7. This is like putting a rubber duck in the river upstream or sending a chat message from one thread to another. Right, so we got a tuple let RX and TX, exact opposite, equal MPSC channel. We have a thread, spawn, move, taking in any piece. We have let value, string from high. Then we simply send it. We send the value and unwrap the option. Again, we're using thread spawn to create a new thread, and then using move to move TX into the closure so the spawn thread owns TX. The spawn thread needs to own the transmitter to be able to send messages through the channel. The transmitter has a send method that takes the value we want to send. The send method returns a result type. So if the receiver has already been dropped and there's nowhere to send a value, the send operation will return an error. In this example, we're calling unwrap to panic in case of an error, but in a real application, we would handle it properly. Return to Chapter 9 to review strategies for proper error handling. Okay, yeah, sure. In listing 16.8, we'll get the value from the receiver in the main thread. This is like retrieving the rubber duck from the water at the end of the river or receiving a chat message. All right, we have received equals rx.recv.unwrap, having received. Print line got, and then the received value. I'm really curious. The receiver has two useful methods, recv and try recv. We're using recv, which is short for receive, which will block the main thread's execution and wait until a value is sent down the channel. Okay, yeah. I was thinking that you'd have to just wait until the thread finished up in order to gain it. But no, you can just wait until it's sent. What if multiple values are sent at different points in time? Will it simply wait for one value and then continue on, even if multiple values would be sent later? Can you send multiple values? It has multiple people who can send a value, so multiple values should be received. I'm assuming try recv simply checks to see if any has been. Once a value is sent, recv will return it in a result. When the transmitter closes, recv will return an error, the signal that no more values will be coming. The try recv method doesn't block. Oh. When the transmitter closes, recv will return an error signal. Okay, so it will wait until all instances of the transmitter or TX are destroyed. Really? Okay, so recv will wait for all different instances of TX to resolve, I'm assuming? Okay. The try recv method doesn't block, but will instead return a result immediately. An OK value holding a message if one is available, and an error value if there aren't any messages this time. Using try recv is useful if this thread has other work to do while waiting for messages. You could write a loop that calls try recv every so often, handles a message if one is available, and otherwise does other work for a little while, for a little while until checking again. We've used recv in this example for simplicity. We don't have any other work for the main thread to do other than wait for messages, so blocking the main thread is appropriate. When we run the code in listing 16.8, we'll see the value printed from the main thread, got high. Wait, so it will always have got. Is got colon a vector? I'm assuming so. Almost certainly that's a vector. Or some other type of list object. List thing. Channels into ownership transfers. The ownership rules play a vital role in message sending because they help you write safe concurrent code. Preventing errors in concurrent programming is the advantage of thinking about ownership throughout your Rust program. Sorry, what? Yeah. Let's do an experiment to show how channels and ownership work together to prevent problems. We'll try to use a val value from the spawn thread after we've sent it down the channel. Try compiling this code in listing 16.9 to see why this code isn't allowed. Use standard sync MPSC and thread. Right, so we've got the transmitter and receiver. We spawn a thread, we get a value called hi, transmitter sends val, and then tries to print val. Why isn't this allowed? Is ownership moved over with the send? Here we try to, what is the error? Can we see what the error is? No, that just tells you, hey, there's no compile. Here we try and print val after we sent it down the channel via tx send. Allowing this would be a bad idea. Once a value has been sent to another thread, that thread could modify or drop it before we could try and use the value again. Okay, so this is always ownership transferring. This can't be, well, I mean, you could probably get it to borrow by just sending a reference, I guess. Right, okay, yeah, so this is like just sending it into any other method, I guess. Potentially, the other thread's modifications could cause errors or unexpected results due to inconsistent or non-existent data. However, Rust gives us an error if we try to compile the code in listing 16.9. Why, though? This is not mutable. You can't change val. The only thing that could happen is if it is dropped, at which point it should be a lifetime error, correct? Borrowing of moved value, val. Move occurs here because val has a type string which doesn't implement copy. Let val, right, send val. Value moved here. Value is moved through the send method. Value borrowed here after move. Is it because this is implementing move? Yeah, because of the move keyword? Um, okay. No, this error originates in this macro, sure. Our concurrency mistake has caused a compile time error. The send function takes ownership of its parameters, and when the value is moved, the receiver takes ownership of it. This stops us from accidentally using the value again after receiving it. The ownership system checks that everything is okay. Sending multiple values and seeing the receiver waiting. This code in listing 16.8 compiled and ran, but it didn't clearly show us that two separate threads were talking to each other over the channel. In listing 16.10, we made some modifications that will prove the code in listing 16.8 is running concurrently. The spawn thread will now send multiple messages and pause for a second between each message. Hi from the thread is a values vector. For every value in the vector, we want to send it and then unwrap the output, and then we sleep. And then for received in Rx, got this. This time, the spawn thread has a vector of strings. Right, so what I'm going to assume is that if we put a print line in here, it has to wait, right? Sure, yeah, it has to wait. This time, the spawn thread has a vector of strings that we want to send to the main thread. We iterate over them, sending each individually, and pause between each by calling the thread sleep function with a duration value of 1 second. In the main thread, we're not calling the receive function explicitly anymore. Instead, we're treating Rx as an iterator. For each value received, we're printing it. When the channel is closed, iteration will end. When running the code in 16.10, you should see the following output with a 1 second pause between each line. Hi from the thread. Because we don't have any code that causes or delays in the for loop in the main thread, we can tell that the main thread is waiting to receive values from the spawn thread. Yes. Creating multiple reducers by cloning the transmitter. Earlier, we mentioned that MPSC was an acronym for multiple producer, single consumer. Oh, never an issue. Hope you get better soon. I'm really sorry to hear you're sick. Wishing you the best. We're not going over anything too bad right now, just multi-threading. Honestly useless, and I don't understand it anyway. Creating multiple producers by cloning the transmitter. Earlier we mentioned that MPSC was an acronym for multiple producer, single consumer. Let's put MPSC to use and expand the code in listing 16.10 to create multiple threads that all send values to the same receiver. We can do so by cloning the transmitter, as shown in listing 16.11. Here's the snippet. All of that. Let tx1 equal tx.clone. We've cloned tx. What's going on? Yeah, okay, that's fine. That's fine. Right, so clone versions of tx will always send to the same receiver. Is that what's going on here? I guess so. I thought we would just... No, it makes sense. It makes sense that we can't pass tx to multiple places. Yeah, that's fine. Right, thread spawn, move. We got the vowels, hi from the thread, vowels and vowels. Yep, send, unwrap. More messages for you in a secondary thread, which is spawned. Hey, here we go. Just hit unwrap. There we go. Then we, for received an Rx, got. So we're probably going to get like an interleave, like hi, more, from, messages, the thread, for you, or something like that. This time, before we create the first spawn thread, we call clone on the transmitter. This will give us a new transmitter we can pass to the first spawn thread. We pass the original transmitter to a second spawn thread. This gives us two values. Oh, what did I do? Oops, sorry about that. This will give us a new transmitter we can pass to the spawn thread. we pass the original transmitter to a second spawn thread. This gives us two threads, each sending different messages to the one receiver. When you run the code, your output should look something like this. Hi, more from messages for the thread U. Yep. You might see the values in another order, depending on your system. This is what makes concurrency interesting as well as difficult. If you experiment with thread sleep, giving it various values in the different threads, each run will be more non-deterministic and create different output each time. Usually it's not because you're running spawn thread or thread sleep, it's because things actually take time. Now that we've looked at how channels work, let's look at a different method of concurrency. Right, here's a quiz. Determine if it passes the compiler and what its output will be. So we're using thread and we're using multiple producers, single consumer, and thread. Enum client message is incur, get, and quit. We have enum server message, get usize, which is a get object. We haven't learned what that is, but I'm glad that they're just pretending we have. Right, so we got server and client server. Right, so we have a transmitter for the server and a transmitter for the client, and then transmitter for the client, or a receiver for the client, and a receiver for the server. We have let server equal thread spawn move. Right, so we got a mutable n equals 0. We got a loop, which just continuously do this. If server, right, so it's going to wait for server receiver to get its message, unwrapping it, and then it matches against quit. If quit, break. If incur, +1. If get, send out the message. And then it's just going to do that forever. Good. For messaging client incur, yep. For all the messages in, and that's not inside of the server, of course. Client message incur in client message incur. This is creating a, this is creating something. I can't really remember. Some kind of list object. Client message incur, client message is this. We have client message get, client's message quit. For each of those, we want client transmitter to send a message, the message. So send incur, get, and quit, which is in an unnamed array, unnamed vector, whatever. If let server message get n. Yep. Client receive equals, right, so client is going to wait until it gets all of the information from this, which is just going to run forever. Is this going to run? Is this going to run? I was just assuming it did. I don't think this runs. Because this is going to be waiting forever, right? This is just looping forever. This is never going to stop. Unless, of course, it's quit. Oh, never mind. We have a quit. I'm an idiot. I am a fool. It'll run 3 times. I'm an idiot. Bit of a dum-dum. That's okay. So yeah, it's fine. That will die. After that dies, this will wait for all the messages which have already been sent. The messages which have been sent don't die, I'm assuming. So we're going to have increase, get, and then quit. We're sending. Then n will be run by a get. We're going to try and get it. Yep, so the get, which is a usize, will be equal, right? When I say right, I don't really know. I believe that this is just going to run perfectly okay. So n equals 0, we're going to add 1, and then we're going to quit. I believe quit will kill this entire thing. However, since the message is sent via server TX, we can client server TX, client receives. Client receives can in fact receive the message even after that's dead. Of course it can. So it's going to receive 1. Because it's only going to increase get. Increases, so that's now 1. Then it gets, sends it out, and then it quits. Which just breaks this loop. Alright, I think that's fine. I think it does, and it'll output 1. Sure. Determine whether the program passes the compiler. Right, so we got a standard multi-producer single consumer and a thread. Let transmitter and receiver equal the channel. Spawn thread, move, let s equal string hello world. We send s.clone dot unwrap. Does s implement the clone? No, yeah, I'm right. Yeah, never mind. It's fine. Yep, so s.clone dot unwrap. So if there's an error, then send the length. Alright. No, I don't think that'll do the thing that you want it to be. Right, so the thread is created. Inside of it, we let s equal string from hello world. We then send a clone of hello world over through tx, which will be just hello world, which this can receive, and then we separately send a length argument. Let s equal rx receive dot unwrap. That's fine. S now equals a tuple or some other type of object I don't know yet that holds hello world and the other thing, which is the length. 7, 10, I don't know, fucking 11, who cares? The number. And then we try this again. We just run it again. I don't think this will have anything. I don't think this will compile. Maybe it will work perfectly fine. Maybe it will work. No, because receivex waits until every single instance of tx is utilized and deleted until it's gone. So no, I don't think that'll work. If tx is all gone, there's no more transmitters, how can it receive? Why would it compile? I got them both correct. Great. Mostly luck. Let's get a bit of a... This does compile, and its output will be 1. This is an example of how to use enums to send different kinds of messages over a channel. Here, the client increments a number, retrieves the number, then exits the server. Right, this will not compile. Channels can only send values of a single type. That's the problem. Okay, that's fair. That's the problem here. So tx.send s.length is a type error. If you want to send values of multiple types, you can either use an enum or the any trait. So can we just call receive twice? I mean, I got it right, but not for the reason I thought I would. Who cares? I'm still correct. I'm a king. Shared state concurrency. We're going to continue on this. Looks like we got a bit of it, but this might be the last thing for today. Who knows? Maybe extensible concurrency with the sync and send trait will be very small. We're going to try and go as long as we can. Shared state concurrency. Message passing is a fine way of handling concurrency, but it's not the only one. Another method would be for multiple threads to access the same shared data. Consider this part of the slogan from the Go language documentation again. Do not communicate by sharing memory. What would communicating by sharing memory look like? In addition, why would message passing enthusiasts caution not to use shared memory? In a way, channels in any programming language are similar to single ownership, because once you transfer a value down to a channel, you should no longer use that value. Shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location at the same time, as you saw in Chapter 15, where smart pointers made multiple ownership possible. Multiple ownership can add complexity because these different owners need management. Rust type system and ownership rules greatly assist in getting this management correct. For an example, let's look at mutexes, one of the more common non-common concurrency primitives for shared memory. Using mutexes to allow access to data from one shared thread at a time. Mutex is an abbreviation for mutual exclusion, as in, a mutex allows one thread to access some data at any given time. To access the data in a mutex, a thread must first signal that it wants access by asking to acquire the mutex's lock. The lock is a data structure that is part of the mutex that keeps track of who currently has exclusive access to the data. Therefore, the mutex is described as guarding the data it holds via the locking system. That's interesting. So it's kind of like a wait your turn thing. Mutexes have a reputation for being difficult to use because you have to remember two rules. You must attempt to acquire the lock before using the data. Compiler will help you with that, I'm assuming. When you're done with the data that the mutex guards, you must unlock the data so other threads can acquire the lock. That's easy to not do. Well, no. Never unlocked could be like an error, if there's other things utilizing it. Very real-world metaphor for mutexes. Imagine a panel discussion at a conference with only one microphone. Before a panelist can speak, they have to ask or signal that they want to use the microphone. When they get the microphone, they can talk for as long as they want to, and hand the microphone to the next panelist who requests to speak. If a panelist forgets to hand the microphone off when they are finished with it, no one else would be able to speak. If management of the shared microphone goes wrong, the panel won't work as planned. Management of mutexes can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. However, thanks to Rust type system and ownership rules, you can't get locking and unlocking wrong. Yeah, so we'll just tell you, hey, you fucked up, boy. As an example of how to use a mutex, let's start by using a mutex in a single-threaded context, as shown in listing 1612. Right, let m equal mutex new 5. Let mute n num m.lock unwrap dereference num equals 6. Right, and then we print m. Right, so m is a new mutex. Inside of this new context, we let a new mutable num equal m.lock.unwrap. I'm guessing that's an option just telling you whether or not you can lock it. Perhaps it's like a wait to lock function or something like that, a method, I guess. And then just, hey, num, dereference num equals 6. And then at the end of this point, num is destroyed. However, this simply pushes back, because this is not captured, this is simply pushed back to m. And m is printable as 6. Exploring, yep. As with many types, we create a mutex using the associated function new. To access the data inside the mutex, we use the lock method to acquire the lock. This call will block the current thread, so it can't do any work until it's our turn to have the lock. It'll lock the entire thread? Okay. This call will block the current thread. Oh, okay, yeah, fair enough. So this thread, well, this entire main thread, if this was inside of a new thread, it would stop that thread. Not all threads, just that thread. Not any thread that implements M or utilizes M, but simply this thread. Alright. The call to lock would fail if another thread holding the lock panicked. And in that case, no one would ever be able to get the lock. So we've chosen to unwrap and have this thread panic if we're in that situation. After we've acquired the lock, we can treat the return value, named num in this case, as a mutable reference to the data inside. The type system ensures that we acquire a lock before using the value in M. The type of M is mutex i32, not i32. So we must call lock to be able to use the i32 value. We can't forget the type system won't let us access the inner i32 otherwise. As you might suspect, mutex is a smart pointer. More accurately, The call to the lock returns a smart pointer called mutex guard. Wrapped in the lock result that we handled with the call to unwrap, the mutex guard smart pointer implements deref to point at our inner data. The smart pointer also has a drop implementation that releases the lock automatically when a mutex guard goes out of scope. That is useful. I like that. That's good, but no buts on that. I think that's good. Which happens at the end of our inner scope. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by another thread, because the lock release happens automatically. After dropping the lock, we can print the mutex value and see that we're able to change the inner I32 to 6. Yep, that's fair. Sharing a mutex between multiple threads. Now, let's try to share a value between multiple threads using mutex. We'll spin up 10 threads and have them each increment a counter by 1. So the counter goes from 0 to 10. The next example in listing 1613 will have a compile error. We'll use that error to learn more about the mutex and how Rust helps us use it correctly. We have standard sync mutex in a thread. Alright, let counter equal a new mutex, let mutable handles equal a vector. 4, 0 to 10. Let handle thread spawn move. So we'll be creating 10 different threads. Let mutable num equal counter.lock on ramp. So this will be the counter. Here. Dereference it plus equals 1, and we'll do that. And then handles.push handle. Yep. So we're capturing handles. Yeah, so handle will be the output of the thread. Which is... Oh god, I can't remember this. What's this thread output again? I can't remember. Yeah, thread outputs a handle for the thread. Yeah, that we can then use to join. Yep, okay, that's fair. Yeah, understandable. We then for handle and handles, handle.join on ramp. Right, but we're spawning like 10 different threads, each that are locking before unwrapping, adding, and then destroying. Okay. I don't really see the issue here. I mean, there is an issue, but why? Then we simply, hey, counter, dereference counter, lock, unwrap. The result is the counter. Okay. We create a counter variable to hold an I32 inside of a mutex, as we did in listing 1612. Next, we create 10 threads by iterating over a range of numbers. We use thread spawn to give all the threads the same closure. One that moves the counter into the thread, acquires a lock on the mutex by calling the lock method, and then adds 1 to the value in the mutex. When the thread finishes running its closure, num will go out of scope and release the lock so another thread can acquire it. In the main thread, we collect all the join handles. Then, as we did in listing 16.2, we call join on each handle to make sure all the threads finish. At that point, the main thread will acquire the lock and print the result of this program. We hinted that this example won't compile. Now let's find out why. I actually don't know. Use of move value counter. Oh, because counter is moved? That's the issue? Yeah, okay, that's fair. Move occurs because counter has type mutex, which does not implement the copy trait. Can we just clone it? Or use multiple owners? We gotta use multiple owners if this is like this mutex, this another thing, right? Right, value moved into closure here occurs because of the usage in the closure. What issue could this have, though, like if it was just allowed to exist as it does? The error message states that the counter value was moved in the previous iteration of the loop. Rust is telling us that we can't move the ownership of lock counter into multiple threads. Let's fix the compiler error with the multiple ownership method we discussed in Chapter 15, with V. In Chapter 15, we gave a value multiple ownership by using the smart pointer RC, and they stated that it does not work with multi-threading, to create a reference that counted value. Let's do the same thing here and see what happens. We'll wrap the mutex in an RC, enlisting 1614, and clone the RC before moving ownership to the thread. Right, we got the same thing here, except we're cloning the RC of counter, reference to counter. And that seems to be the only real difference other than handling that it's an RC. Nope, we don't even have to handle this. An RC, I forgot about that. Once again, we compile it and get different errors. The compiler is teaching us a lot, is it? Ooh, that is a funky little error. RC mutex R32 cannot be sent between threads safely. Right, within this closure, main, required by a bound introduced by this call, thread spawn, RC mutex R32 cannot be sent between threads safely. Help, within closure, the trait send is not implemented for RC. Okay. Note, required because is used within this closure. Okay. Required by a bound in spawn. Note, required by bound in spawn. Wow, that error message is very wordy. Here's the important part to focus on. RC mutex R32 cannot be sent between threads safely. The compiler is also telling us the reason why. The trait send is not implemented for RC mutex I32. So it doesn't know what to do in order to pass this to multiple threads. We'll talk about send in the next session. It's one section. It's one of the traits that ensure the types who use this thread are meant for, in concurrent situations. Yep. Unfortunately, RC is not safe to share across threads. When RC manages the reference count, I understand why, because if it's put up through multiple threads and it tries to add it up, each RC will not, in fact, perhaps hold the same count. It adds to the count for each call to clone, and that's not a mutex, and subtracts from the count when each clone is dropped. But it doesn't use any concurrency primitives to make sure that changes to the count won't be interrupted by another thread. So two threads could try and add at the exact same time. This could lead to wrong counts. Subtle bugs could in turn lead to memory leaks or a value being dropped. You're awake now? Hello! Welcome in! Oh, sadly we're quite close to ending. I'm sorry to see. We'll continue on forward though. We're currently learning how to make applications that will kill us mentally and physically as we try and figure out what the hell's wrong with them. It's trying to tell me that it'll fix it all for me, but I don't believe them so far, honestly. Still, though, I'm glad to see you in here. Oh, yeah, I forgot we do have VODs up. It's good to see. Right, what are we looking at? Unfortunately, it doesn't share. Yeah, it doesn't use any concurrency primitives. Right, this could lead to wrong counts, subtle bugs that could in turn lead to memory leaks. What we need is a type exactly like RC, but one that makes changes to the reference count in a thread-safe way. Okay, I'm glad that they take these two things apart, because using a mutex likely causes some, slowness. Of course, there's more work being done in order to have a mutex, so that needs to have more work done, and thus having, a secondary RC in order to use mutex is good. I like that. Atomic reference counting with arc. Okay. Fortunately, arc is a type like RC that is safe to use in concurrent situations. The A stands for atomic, meaning it's an atomically referenced counted type. Atomics are an additional kind of concurrency primitive that we won't cover in detail here. See the standard library documentation for standard sync atomic for more detail. At this point, you just need to know that atomics work like primitive types, but are safe to share across threads. Okay? You might then wonder why all primitive types aren't atomic, and why standard library types aren't implemented to use atomic by default. The reason is that thread safety comes with a performance penalty that you only want to pay when you really need to. If you're just performing operations on values within a single thread, your code can run faster if it doesn't have to enforce the guarantees atomic provides. So the guarantees are run on during runtime. Can we fuck up on this? Can Does it fix these guarantees? Does it alter how the code behaves in order to ensure that the code is thread safe? I guess it would have to, because otherwise it would just be doing it at compile time and have no performance penalty during runtime. I guess so, yeah. Let's return to our example. Arc and RC have the same API. So we fix our program by changing the use line and call the and the call the new and the call the clone. The code in listing 1615 will compile and run. So we simply put an A in front of RC, arc new mutex, and arc clone the counter instead of RC clone the counter. And that is the only real change here. I guess using arc is just the decision to have poor performance, worse performance, in exchange for concurrency in this form. I wonder what the differences are between messaging and between shared memory like this. I was thinking that perhaps shared memory would be quicker, but now with this information, perhaps shared memory is slower, if done incorrectly, because during messaging, you have to wait. You have to wait until it finishes up in order to get that information. With shared memory, you can likely have a situation where waiting isn't really necessary. Much easier than with messaging. However, shared memory has a performance penalty by default. Okay, I think I can understand the pros and cons of this, or at least some of them. Code will print the following: result 10. We did it! We counted from 0 to 10, which might not seem impressive, but it did teach us a lot about mutex and thread safety. You can also use this program structure to do more complicated operations than just incrementing a counter. Using the strategy, you can divide a calculation into independent parts, split those parts across threads, and then use a mutex to have each thread update the final result with its parts. Note that if you are doing simple numerical operations, there are types simpler than mutex. Types provided by the standard atomic module of the standard library. Okay, I'm really curious about these, and I want to look at them. These types provide safe concurrent atomic access to primitive types. This code creates 10 threads. Yes, it does. Yep, 0 through 10, just 10 entire threads being built up. Of course, if you don't have a processor with 10 cores, it doesn't do much, but really it seems that multi-threading here is a hell of a lot simpler than any other language. Yeah, anything that I've seen before. Of course, I'm not very learned in like multi-threading, but a hell of a lot more easy. Just 10 threads through this. Just a for loop with handle spawn each thread within the for loop. Yeah, that's easy. We did it. Note that. Yep, I'm really curious about this. I really want to know. What are some of these simpler accesses? Atomic U16, U8, and ordering? I guess I'll look at that later. But I'm really curious. You might have noticed that counter is immutable, but we could get a mutable reference to the value inside of it. This means mutex provides interior mutability. Yeah, you tried it with Python and made you want to give up several times. Completely understandable. Python can get incredibly complicated if you want it to, and the second you get multi-threading in any different application, it's just hell. This is why I'm a JavaScript developer. We very rarely have to worry about performance in any way, shape, and or form. Or multi-threading. I've never tried multi-threading in Python, though. I kind of want to. You might have noticed that, yep, interior mutability is just built into mutex. I don't know how to feel about that. In the same way we use refcell in chapter 15 to allow us to mutate contents inside of an RC, we use mutex to mutate contents inside of an arc. Okay, yeah, I guess that's fair. Another detail to note is that Rust can't protect you from all kinds of logic errors. When you use mutex, recall in Chapter 15 that RC came with the risk of creating reference cycles, where two RC values refer to each other, causing memory leaks. Similarly, mutex comes with the risk of creating deadlocks. These occur when an operation needs to lock two resources and two threads have each acquired one of the locks, causing them to wait for each other forever. If you're interested in deadlocks, try creating a Rust program that has a deadlock. Then research deadlock mitigation strategies for mutexes in any language and have a go at implementing them in Rust. The standard library API documentation for mutex and mutex guard offers useful information. I really like that. That is really cool. That is a very interesting thing to suggest. Like, hey, try and cause the breaking situation, and don't look up how do I do X in Rust. Look up how do I do X in Python? How do I do X in Java? So on and so forth. And then try and implement it in Rust. That is a really interesting way of putting it, of trying to challenge the person reading. I like that a lot. All right. We'll round out this chapter by talking about the send and sync traits and how we can use them with custom types. 2 questions. Question 1. In some currency APIs, a mutex is separate from the data it guards. For example, imagine a hypothetical mutex API like this. Let mute data equal a new vec. So that's what deadlock means? I guess so, yeah. That's just, hey, two things want the data, and neither of them can get it because both are asking for it. So you're just in a deadlock. Terrible time. Yeah, so we have a mutex. We have data, which is vector, a mutex, which is a new mutex inside of a new, what is it called? Scope. Let underscore guard equal mx.locked. We have locked guard. Then we push the data. Which of the following best describes why Rust uses mutex instead of just, mutex of any type instead of just mutex? What? In some concurrency APIs, a mutex is separate from the data it guards. For example, imagine a hypothetical mutex API like this. Okay? To acquire fewer calls to mutex methods? No. There's the same amount that we'd have to do. To provide the efficiency of concurrent programs with mutexes. To improve the efficiency of to prevent a mutex's data from being moved between threads. No. To prevent accessing a mutex's data without locking the mutex? What? I'm sorry? I don't understand what it's even asking. In some concurrency APIs, the mutex is separated from the data it guards. Okay, so the mutex would be, hey, this creation of mutex here, which you can then lock at a different point. Data is not pushed into mutex at any point in time. So mutex is just created, like guard equal mx lock, and then data push. I guess this would in fact defend it. I see. I think I see. So what it's saying is that in other languages, what you would do is if you were trying to access data, you would ask the mutex, is it currently guarded before accessing data? However, since it's not part of the mutex type, since it's not part of data, since data is not in any way itself checking, somebody could just ignore that underscore guard exists and ignore that it is locked and still simply push. So I believe the best thing here is preventing access in mutex's data without locking the mutex. Submit. Alright, second question. Determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. We have standard, arc, and thread. Let s equal string hello world. Let a equal a new arc from the reference string. Let a2 equal arc clone of a. So we have two owning values. We have a and a2, which both own s. No, sorry. We have A2, which owns A, and A owns S. Okay, sorry. We have a new thread. The thread is spawned utilizing the move within this closure. We just get A2.length and pass back. Right? Length equals t.join.unwrap. I don't see why this wouldn't compile. Why would this not compile? Let me think. Arc is fine for multiple owners with multi-threading. That is okay. We are cloning A and S. You can clone an RC, create a new version of the RC. You can hold inside of an RC. I know that. I'm pretty certain on that. I see no reason why this would be an issue. Unless it's going to say like A2.length is not a method that can be utilized on A2 because it doesn't go all the way down, but I know it does go all the way down. So I see no reason why this wouldn't be able to compile. A. Right. So let me think. A. A currently owns itself because it's utilizing A, not A2, which there's no issue on because A can still own itself because it's an arc, right? Okay, this may be why it says it doesn't compile. I may misremember. Perhaps the issue is that A2 has ownership over A, and you can create multiple pieces that have ownership over A. However, you cannot utilize A until A2, and all of the other things owning A are gone. But still, I believe this will compile. I could be wrong, though. I could very well be wrong. So it is printing out A, which will print out Hello World, with capital H. I see no reason why this would not work. And then the length. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Honestly, I think this might not compile now that I think about it. But hey, we'll learn very quickly. It doesn't compile. Preventing access to mutex's data without blocking the mutex. Right, so I guess I'm correct on that. That's good. That is the issue. Secondarily, it does not compile. And the reason, I'm going to guess before reading the context, is because you cannot access A when an arc of A exists. You can have multiple arcs of A, but you cannot access A. An arc is still not safe to use if its data contains a reference. I'm an idiot. Since the reference could, in theory, be invalidated before all threads containing the arc finish executing. It didn't explain this before, but I do understand why. I was wrong on the reason why. I wasn't even close to even thinking about this. It is the reference that is at issue. The arc must own its data. Otherwise, since it's just borrowed, you have ownership over the borrowed reference, but you don't have ownership over S. I was wrong here. A does not own S. A owns a reference to S, which is not S, meaning S can be destroyed before the thread finishes. If we waited an hour in here, it would end, and then S would be destroyed. But so would the thread, of course, but we could drop it here. We could drop it before the print line, and it would cause issues. Okay. I think I understand now. That makes a lot of sense. Why allow Arc to take in references at all, then? Arc is only for multi-threading, and you cannot use multi-threading with references in this fashion, so why utilize an arc at all? Sorry, why allow for an arc to utilize this at all? Well, I guess perhaps that's the issue. Maybe arc will say this just outright here. Maybe the error will be here. But I think the error would be here. They would just... who knows? Still, though, that is a good lesson. That is a good lesson. You cannot put a reference into an arc, because that's borrowing, not ownership. And an unowned thing being put into a thread could be changed before the thread is utilized. Okay. Right. So we've got half an hour to go, and we've only got this. This is fairly small. Yeah, I think I'm going to read this, and then we'll be done for the day. Extensible concurrency with the sync and send traits. Interestingly, the Rust language has very few concurrency features. Almost every concurrency feature we've talked about so far in this chapter has been a part of the standard library, not the language. Your options for handling concurrency are not limited to the language or the standard library. You can write your own concurrency features or use those written by others. However, two concurrency concepts are embedded in the language: the standard marker traits, sync and send, allowing transference of ownership between threads with send. The send marker trait indicates that ownership of values of the type implementing send can be transferred between threads. Almost every Rust type is send, but there are some exceptions. What? Almost every Rust type is send. That is a weird thing to say, I guess, but okay, let's just continue anyway. But there are some exceptions, including the RC. This cannot be send, because if you clone an RC value and try to transfer ownership of the clone to another thread, both threads might update the reference count at the same time. For this reason, RC is implemented for the use in single-threaded situations where you don't want to pay the thread-safe performance penalty. Therefore, Rust type system and trait bounds ensure that you can never accidentally send an RC value across threads unsafely. When we tried to do this in listing 1614, we got the error: the send trait is not implemented for RC mutex I32. When we switched to ARC, which is send, the code is compiled. Any type composed entirely of send types is automatically marked as send as well. Almost all primitive types are send, aside from raw pointers, which we'll discuss in chapter 19. Allowing access from multiple threads with sync. The sync marker trait indicates that it is safe for the type implementing sync to be referenced from multiple threads. In other words, any type T is sync if reference T, an immutable reference to T, is send. Okay, meaning the reference can be sent safely to another thread. Similarly to send, primitive types are sync. The types composed entirely of types that are sync are also sync. I'm sorry. This I do think I understand. However, the way it's written is incredibly confusing. I've worked with a lot of non-English first language people, and this would kill them. This is, I don't know how to write it in a better way, but I wish they didn't reference it as it is sync. I don't see where that became a thing, why we started calling things sync or send. Whatever. Sync is the most similar concept in Rust to the colloquial meaning of the phrase thread safe, i.e., that a particular piece of data can be safely used by multiple concurrent threads. The reason for having separate send and sync traits is that a type can sometimes be one, or both, or neither. The smart pointer RC is also neither send nor sync, for reasons described above. The ref cell type, which we talked about in chapter 15, and the family of related cell types are send, meaning you can utilize it inside of a thread. If T send, or send if the type is also implementing send, but they are not sync. A ref cell can be sent across a thread boundary, but not accessed concurrently, because the implementation of borrow checking that ref cell does at runtime is not thread safe. A smart pointer mutex is send and sync, and can be used to share access with multiple threads, as you saw in sharing a mutex between multiple threads. The type mutex guard that is returned by mutex lock is sync. Of course, yeah, it can't be sent to multiple threads. How could that work? But not send. It is specifically not send because some platforms mandate that mutexes are unlocked by the same thread that locked them. Some platforms mandate that mutexes are unlocked by the same thread that unlocked them. I wonder what it means by platforms. Is that like the Linux operating system? Not sendable, to quote the standard. If a thread attempts to unlock a mutex that has not locked or a mutex which is unlocked, undefined behavior results. Okay. What? I'm just curious about what specific platforms. Once more, I click a link and then don't actually follow through with it. Either way, hey, let's go forward. Implementing send and sync manually is unsafe. Because the types that are made up of send and sync traits are automatically also send and sync, we don't have to implement those traits manually. As marker traits, they don't even have a method to implement. They're just useful for enforcing invariants related to concurrency. Manually implementing those traits involves implementing unsafe Rust code. Really? Okay. We'll talk about using unsafe Rust code in Chapter 19. For now, the important information is that building new concurrent types, not made of send and sync parts, requires careful thought to uphold the safety guarantees. The Rustonomicon, again, love that name, has more information about these guarantees and how to uphold them. As a summary, this isn't the last you'll see of concurrency in this book. The project in Chapter 20, very excited for that, will use the concepts of this chapter in a more realistic situation than the smaller examples we've discussed here. As mentioned earlier, because very little of how Rust handles concurrency is part of the language, many concurrency solutions are implemented as crates. These evolve. Uh-oh? Oh no. These evolve more quickly than the standard library, so be sure to search online for the concurrent state-of-the-art crates to use. What's wrong? I'm sorry, with the delay, I really don't know what that was for. I can understand just in general, though. Yeah, to be honest, I thought I understood it at first, but I don't really understand all of this. Oh, yeah, smart pointers, fully understandable. Only way to get better is to just head right in, use them as much as possible. I'm not good at smart pointers either, to be clear. The Rust standard library provides channels for messages, passing, and smart pointer types. Absolutely, I'll have to reread too. Especially with this. I'm gonna have to reread this tiny page like 20 times to fully understand what's going on here. But hey, that's programming, isn't it? Alright, so the Rust standard library provides channels for message passing and smart pointer types, such as mutex and arc, that are safe to use in concurrent contexts. The type system and the borrow checker ensure that code using these solutions won't end up with data races or invalid references. Once you get your code to compile, you can rest assured that it will happily run on multiple threads without the kinds of hard to track down bugs common in other languages. Concurrent programming is no longer a concept to be afraid of. Go forth and make your programs concurrent, fearlessly. Oh wow, thank you. Next, we'll talk about idiomatic ways to model problems and structure solutions as your Rust programs get bigger. In addition, we'll discuss how Rust idioms relate to those you might be familiar with from object-oriented programming. Okay, and now we have a one-question quiz. Imagine you are designing an API for a database connection like this. You have a struct with a database connection. Implemented on the database, we have a query, taking in self, and returning result. Your database does not support concurrent queries from the same connection. Which of the following marker traits should DB connection implement? Does not support concurrent queries from the same connection. Okay, so send seems to be fine, but sync does not seem to be fine. Sync would be concurrent in the same connection, like lock, meaning that data would be shared between different pieces. But send allows you to send multiple threads, send information through multiple threads. Which of the your database does not support concurrent queries from the same connection. Yeah, send does seem to be fine, but does not support concurrent queries from the same connection could mean that if you passed it to another thread, this would be another connection, because sending the DB connection. No. That is right. Because sending the DB connection kills it within your current thread. So send is the only answer. Yep, that is correct. Context? It is fine to send a DB connection between threads, so DB connection should implement send. But it would not be valid, for example, for an ARC database to be shared such that multiple threads concurrently called db.query. So DB connection should not implement sync. All right, and that is the end of this chapter. I think this is the first chapter in a while we've actually gotten through in a single session. Yeah, this was fun. I enjoyed this one. I like this one. I like how they made concurrency and multi-threading have the fewest amount of random pieces of trash that I've ever seen. Though I'm certain that if I went on Crazy.io, I would find an insane amount of stuff to do with concurrency. Or if I read the entire sync arc thing, sync atomic thing, we would get that. Next time, however, we are going to learn how to pretend to be object-oriented programmers in Rust. Fantastic. I've never really seen in like C, C++, etc. people actually fully utilize object-oriented as it should be. People tend, if they have the ability to break the paradigm, do break the paradigm. But maybe that's a good thing. I'm just a bit, I'm a bit stuck in my ways, I guess. If you choose OOP, use OOP. Still, though, this is very cool. This is going to be really easy to understand, I'm assuming. We'll have a bit of a break finally. Anyway, I think that's it for tonight. Thank you for jumping in at that last half. I hope you can understand the rest of it too. Anyway, goodbye. I'm going to end stream now. I'll see you in a week if you're available. Goodbye. This never stops.